In this video, we'll be going over the solutions to lab problems from week 4. So this lab is really focused on elementary matrices and finding determinants, aka cofactor expansion of matrices. So our first question here has to do with elementary matrices. So we'll quickly talk about what these actually are before we get into solving the problem. So an elementary matrix, you can think of it as a row operation in matrix form. Okay, so that's all it is. It's one single, so I guess I should say one single. It's not multiple, it's just one single row operation in matrix form. Okay, so I'll give you a quick example of that. I'll do it over here so I don't run out of space later. But if I had a row operation of switching row 1 and row 2. So what I would do to find the elementary matrix that corresponds to that is I would take the identity matrix. So I'm always, when I'm using elementary matrices, I'm always starting with the identity matrix, and I'm applying that exact row operation to the identity matrix to get my elementary matrix. Okay, so I have my identity here, and I'm switching row 1 and row 2. That's my operation, and I'm going to end up with just exactly that when I switch row 1 and row 2 in the identity matrix. So this right here, this guy right here, that's my elementary matrix corresponding to that row operation. Okay, so I'll do one more kind of over here. So same thing, if I have, what should I do of a row operation? I'll do row 1, I'll do plus row 2. Okay, say that was one of my row reduction steps or my row operations. So what I'm going to do to encode this in matrix form, so make an elementary matrix out of this, is I'm going to just start with my identity matrix here, and I'm going to apply this row operation to my identity matrix. So I'm adding row 2 to row 1 here. So I'll end up with something that looks like this. Oops, not like this, I'm sorry. Like this. All right, so this one is my elementary matrix right here, corresponding to this row operation. Okay, so when you do elementary matrices, you're always starting with the identity and applying that specific row operation to your identity matrix, and then whatever you end up with, that's your elementary matrix. Okay, so I hope that makes a little bit of sense. It's kind of strange, but useful, and especially questions like these. So it's asking us, this one is asking us to, so it gives us our A right here. This is our A, and it's asking us to write A as a product. So a product here, so that means multiplication of 3 elementary matrices. So it's saying that I want you to find 3 elementary matrices that when you times it by, when you multiply them together here, so I want you to find 3 elementary matrices that when you times them together, they equal to A. Okay, so I'm going to introduce you guys to one of the formulas that I believe you're given, which is B equals U times A. Okay, and here your U is just the product of your elementary matrices. So your U is just, it would be, in this case, it would be all 3 of these guys multiplied together. So it's just all of the elementary matrices multiplied together. Your B is what you want, is essentially what you want to end up with, and your A is what you have. Okay, so in this case, what we have, our B is the identity matrix. And the reason it's the identity matrix is because the matrix that we're starting with here, like we're given A and we're not given any other matrices. So what we're going to want to do is we're going to want to use the identity matrix to somehow take us to A. Okay, and this will make more sense when we do it a little bit later, but I'm just showing you guys the formula here first. Okay, so in this case, we would have the identity, and because we need 3 elementary matrices, we have the identity equals, we're going to have E3 times E2 times E1 times A. And the reason that it's in reverse order is because when we do these things, we're always multiplying by the elementary matrix on the left of A. So that means like if you have this one and it's encoding some sort of row reduction step, you multiplied it on the left of A, and then the next step will be on the left of that, and then the next step will be on the left of that. So it goes in kind of reverse order here. Now, in our case, what we actually want to end up with is A. Okay, so this is what we want to end up with. So we want to have A equaling something, right? Because what we want here is we want it to be the product of 3 elementary matrices. We want to express A as that. So we want A to equal some elementary matrices. So in this case, what can we do to isolate for A? Well, we can just take the inverse of this guy. And when you take the inverse of multiple matrices, remember that the order is reversed. Okay, and that's just a rule that you guys, that actually we went through that in the last lab. Or is it this lab later? Anyway, we'll go through it in this lab also. But yeah, so we end up with this multiplied here. So we're multiplying by the inverse of this over here. And just anything multiplied by the identity is just itself. So this is what we end up with right here, this formula. So we know that somehow we have to find 3 elementary matrices when we take A to the identity, and then we have to find the opposite of those guys that will be expressed in terms of A. Okay, so yes, that's all kind of very confusing, but once we do the example, it will make more sense. So we have A here, and our A equals 0.513. Okay, the first, what we're going to do is we're going to take it to the identity matrix here. So we're going to do row reduction. Okay, so first step that I'm going to do is I'm going to switch the rows here. Okay, so we end up with something like this, and the reason I switch the rows is because I want to get this leading one into this position. Okay, my next step that I'm going to do is I'm going to multiply row 2 by 1/5, so I can get rid of that 5. And next step is I'm going to subtract 3 row 2 from row 1, and that will just leave me with the identity matrix. Okay, so you can see here we needed 3 elementary matrices, and I do have 3 row operations, so we're already on the right track here. Okay, so what is this actually telling us? Okay, so it's telling us that if I do these 3 row reduction steps, it gives me the identity. It takes me to the identity. Okay, so if we kind of think about this, if I wanted to go from the identity to A now, if I took the opposite operations of these guys here, then if I multiply them all together, will that give me A? Well, the answer is yes, it will. So that's exactly what we're saying over here. Okay, so over here. So once again, we're taking A and we're doing these row reduction steps here, and it's giving us the identity. Well, what if we want to do it the opposite way? So we want to start with the identity matrix, and somehow we want to get A out of it. Well, what I can do is just take the opposite row reduction steps here. So you can see here I have the inverses written here, which essentially it's meaning the opposite. So I'm going to try and figure out what the opposite of these matrices are, and that will give me my A. So first thing that we have to do is we have to find what our elementary matrices are corresponding to our row reduction steps. Okay, so that was just kind of the overall idea of what we're doing here. So my first elementary matrix is I'm switching row 1 and row 2. And did we do this above? I don't remember, but anyways, so we are applying this to the identity matrix. So of the identity matrix, when you switch row 1 and row 2, it gives you something that looks like this, right? Same thing with our second operation here. If we're thinking about the identity matrix, this guy here, and we're multiplying the second row by 1/5, then we get something that looks like this. So this is our second one here. So I'll just highlight them so they're not confused. Okay. And same thing here. We start with our identity, and if we took row 1 minus 3 row 2, what we would end up with is just 1, -3, 0, 1. Okay, so these are our elementary matrices. So in other words, if you multiply all three of these guys together, by A, it's going to give you the identity. But we want the opposite thing, right? So we want to be able to multiply 3 matrices together, and they give us A. So we want to do this sort of thing here, and it's equaling A. So what we're going to do is we're going to look over here to our formula and think about what we just talked about, that we want to kind of do the opposite thing. And we're gonna actually find E1 inverse, E2 inverse, and E3 inverse. Okay, so to do that, all we're gonna do is what we just talked about of finding the opposite action. Okay, so we have E3 here, E3 inverse. Okay, so we look, once again, we're trying to get from the identity all the way to A. So we've got to, instead of doing this guy here, we've got to do this guy here. So the opposite of whatever we did in the row operations. So we'll start with our first one here. We have row 1 switching with row 2. Now, what's the opposite operation of that? Well, we could do row 2 switching with row 1. And that's technically the opposite, even though it results in the exact same thing here. So our E1 inverse is just is the same thing in this case. But our E2 inverse here, well, let's think about what's the opposite of multiplying something by 1/5. Well, the opposite of multiplying something by 1/5 is multiplying it by 5. So in this case, our opposite action is going to be row 2 times 5. So we have 1, 0, 0, 5. That's what we end up with. And finally, this one right here. We have row 1 minus 3 row 2. Well, what's the opposite of subtracting 3 row 2? Well, the opposite is adding 3 row 2. So this one would be row 1 plus 3 row 2, right? So we would end up with something that looks like this. Okay, so going back to our formula here, we can have A equaling E1 inverse, E2 inverse, E3 inverse. Okay, and we do have these three matrices right here. So what I want you guys to do is I want you guys to try multiplying these three out. Okay, so these three guys here, try multiplying them out and make sure that you do indeed end up with A. Okay, so when you approach these problems, you really have to consider this formula here. So B equals UA, where U is elementary matrices, and you have to figure out what do you want. So in this case, we did want to have A isolated, so we had to multiply by the inverse here in order to get A by itself. Okay, and that's because our B here ended up, it was the identity matrix. So I hope that made a little bit more sense. These questions are kind of difficult when you first start them, but if you practice them, then they'll become much more routine. Okay, so similar question in that we're dealing with elementary matrices, but this one is a little bit different than what we did in our last one. And we can see that by looking at our formula here. So we have B equals UA, and we can see in our question that in fact we're not dealing with the identity matrix anymore. Well, we are still dealing with the identity matrix, but I'm saying that we're given an actual B this time. So our B is not the identity matrix. So this question is asking us to essentially to find the series of elementary matrices that turn A into B. Okay, so I'll explain that a little bit better here. So U is our series of our product of elementary matrices, right? So this is our product of elementary matrices, and what do elementary matrices mean? Like, what do they encode? Well, we know elementary matrices encode row operations. Okay, so essentially, if we think about it in that way, what this problem's asking us to do is it's like, okay, here's a B. Okay, I want you to find this guy here. So I want you to find all of these row operations that I can do to A that turn it into B. Okay, so I'm going to write that here. So I want you to find all the row operations that take A to B. And why do we want to take A to B? Well, because we're doing the row operations on A and we want it to equal B. So we want the product of these row operations multiplied by A to give us B. So because of that, same as last question when we kind of took A into the identity, we're going to do the same type of thing here, except for now what we're going to do is, because we want to find the row operations that take, so the row operations, aka the elementary matrices that take us to B, then what we're going to do is just that. We're going to find what these row operations are. So we have A here trying to take it to B. So first thing I'm going to do is I am going to switch the rows. Okay, so I'm going to end up with something that looks like this. Okay, and next step that I'm going to do is I'm going to multiply the second row by -1, so I can get rid of that negative here. Ends up being looking like this. And next step, I'll write it over here. Actually, no, that's going to be too messy. I'll write it over here. Next step I'm going to do is row 1 plus 3 row 2. and I'll end up with this. And if we look up here, we see that yes, this one equals B. So we've gone from A here. So we've gone from A here to B over here, which is exactly what we wanted to do. So I'm going to highlight these guys here. These are our row operations that take us from A to B. And just like in the last question, what we're going to do is we're going to figure out what the corresponding elementary matrix to these row operations are. Okay, so switching row 1 and row 2 will result in an elementary matrix that looks like this. And multiplying row 2 by -1, think of just multiplying the second row of the identity by -1, and you see that it looks like this. And the last operation is we're just adding 3 row 2 to row 1, so it's going to look like that. Okay, so we have E1, E2, and E3. Okay, so in this case, so in the last case, you remember that we had to find the inverses. Now, why did we have to find the inverses for the last one? Is because we wanted to write A as the product of these elementary matrices. Okay, so we had to like go backwards and figure out what the inverse of it was so that we could write it A as that. But now we see that, okay, well, we actually want to write, like, we want to find B here. We want to write B as the product of elementary matrices, right? So we don't have to do the inverses here because we're already going in the right way. We're going from A to B. Okay, so when we write something like this is we see that right here we have our elementary matrices, and all we have to do for that is remember that I discussed quickly in the last question that when we do this, we're multiplying by A on the left. Okay, so that means that if I have, if I have A here, I'm multiplying on the left by my row operations, or aka my elementary matrices. So because of that, you can see that it's actually in reverse order here. Okay, so because I have A and then I have E1, I can't just multiply E2 right in here because I've already multiplied E1 here. There's no space here, so I have to go to the next position. And similarly, then I have to go to the next position. So it's in reverse order. Okay, it looks a little bit weird, but it works. Okay, so we have, knowing this, we have B. So we have our B here. It's actually equaling to, we're going to end up with our E3, E2, E1, A. Okay, does that make sense? Because like we just discussed, we're multiplying on the left by all of our operations here. And so it's in reverse order. So we get something that looks like this. Oops, that's not a highlighter. So we get something that looks like that. So the question is asking us to find the matrix U such that UA equals B. Well, since we know that U is the product of elementary matrices, all we have to do is multiply these guys together, and that gives us our U. Okay, so what we end up with here, if you multiply all 3 of these together, so U is going to be E3, so E3 times E2, so E2 here, times E1, and our U in this case is going to equal to -3, 1, -1, 0. So this guy here is our U. Okay, so that's the solution to our question. So we would write like this one equals u. So you guys should verify that, in fact, when you do something like this, you should make sure that b does equal u times a, and in this case it does. But there's always a check that you can do if you're doing an exam or something like that, just to make sure that you do have the right matrix here. So once again, the reason why we didn't have to find out the inverses of this is because we wanted to go from A to B, and that's already the order that we went into. Now, if we wanted to go from B to A, then we would have to find the inverses of them, of our elementary matrices, okay? Okay, so we're going to be switching gears a little bit in this question, and we're going to be talking about determinants. So determinants, the formula for a determinant that I like to use is, I like to think of it as sine times whatever left. Okay, so this is what I use to figure out what the determinant is. Traditionally, we have something like I plus, or negative 1 to the I plus j times the minor aij. Okay, so I'll explain what this means actually right now. So we have something that looks like this, our matrix, 2, 1, 3, and 2, 1, 1. Okay, so when we're finding determinants, essentially what we want to do, and right here we're asked to expand along the second row, so what we're going to do is we're going to do that just to keep consistent with what we're supposed to. So this is our second row here. Okay, what we want to do is we want to expand along this row in order to find our determinant. Okay, so what that means is we're going to take each entry in here and we're going to kind of expand with that entry. So before we do that, we're going to talk about this sign thing here, like this negative 1 to the I plus j, or sign right here. So that's just referring, the I plus j is just referring to our position in the matrix. So right here, our I plus, we have our I here and our j here. So our I plus j here is, our position is essentially we have 1 plus 1 equals 2, right? So right here, our I plus j is equal to 2. So in this position, we have, we're in the first row, so 1, 2, we're in the first row, so 1, and we're in the second column, so 2. So our I plus j is equal to 3. Okay, so in this row and column right here, we're in the first row, so we have 1 plus, and we're in the third column here, so 1 plus 3 equals 4. Okay, so if we keep going this way, we're going to find out that it kind of follows this pattern here. So we see that right here we have an even, right here we have an odd, right here we have another even, and it's going to follow that pattern throughout this whole matrix here. So I'm going to just write these signs. So we're going to have plus, minus, plus, and then we're going to have minus, plus, minus, and then plus, minus, plus. So you can really, just to not have to do this thing, you can just write these in. Like if you get a 3 by 3 matrix of any kind, or a 2 by 2, whatever, or 4 by 4 even, if you get a matrix like that, just write in your signs like this quickly. So you always can check if you don't remember, okay, what is the I plus j in the first position? So I always have 1 plus 1, it equals 2. So from there, you're just alternating the signs of your entries from there on in. Okay, so that's what I do at the beginning. So I do plus, minus, plus, and then minus, plus, minus, etc. Okay, so we have our whole sign thing here sorted out. Now the minor aij part. So aka whatever's left. Okay, so when we expand along a row, what that means is, so we have our sign here. So so whatever column, okay, whatever column and row your number that you're expanding is in, what you're going to do is you're going to kind of cross them out like this. You don't have to physically cross them out, but maybe like cover them up with a pencil or your hand or something to start with. So you have, so you're expanding along the second row. So your first entry of the second row though is 2. And you know that the sign of 2 is negative because remember you figured out the signs up there. So you have your -2. So that's your sign and your entry. Now you have to multiply it or find the determinant of whatever is left. So you can see whatever is left when you cross out those 2 rows are these guys right here. So you have 2, 1, 1, 1. Okay, so that's just the first entry here. So let's see if I can erase this without erasing everything. Yes, I can. Okay. Okay. So similarly, we want to move to our next position because remember, we're expanding along this row. So we want to move to our next position here, which is a 1. Okay, so we know that the sign of this is plus because we already figured out all of our signs here. So we can write +1. So we want to write plus our entry. And then what we're going to do is kind of cross this out. Okay, so we can see what's left. So we can see this one's not crossed out, this one's not crossed out, and either are these guys. So our whatever's left portion is going to look like this. Okay, and last one that we're doing is we're expanding with this 3 in mind. So we know that the sign here is negative. Okay, so we have to add a -3 out here, and we're multiplying that by whatever is left. So we got to get rid of the row and the column that 3 is in, and you see that these are the entries here that are left. So we have 1, 2, 2, and 1. Okay. Okay, so because there's no entries left to expand in that row, there's no more entries in here, we're done with the whole expanding. Now all we have to do is to compute the 2x2 determinant. And 2x2 determinant, the formula for that is AD minus BC, or minus CB. So we have, so this is our A entry here, B, C, D. So all we're going to do is we're going to have our -2 out here. Okay, that doesn't change. But we're going to do AD, so 2 times 1 minus 1 times 1. All right, so that's just, we're doing A times D, and we're minusing C times B. Okay, that's just the formula for a 2x2 determinant. So now we're adding our +1, and we're multiplying it by 1 times 1. So 1 times, I'll do this in one bracket, 1 times 1, and we're minusing 2 times 1. Okay, and same with the last one here. We have our -3 out there, and we're going 1 times 1, and we're minusing 2 times 2. Okay, so next up for this one is we just simplify. So just simple arithmetic here. So we end up with -2, and this whole thing in here, this guy here simplifies to 1. And we'll just do it over here. +1 times this guy here simplifies to -1. And this guy here simplifies to -3. Okay, so what we have here is it ends up that this whole determinant equals 6 when we add everything up. So it equals 6. Okay, so I hope that wasn't too confusing. Determinants, they take a little bit to get used to, just like everything else new that you're learning in this course, but the main idea is if you have a 3x3, your first step is, so your first step is, what I want you to do is to label the signs here. So this is a plus, minus, plus. minus, plus, minus, plus, minus, plus. So that's your first step. I want you to label the signs here. Your second step is to figure out which row or column you want to expand on. If there's any columns or rows that have zeros on it, it's a good idea to expand on that one because it's less work, less adding things up. So in this case, we expanded along the second row here. Okay, so that just means that we want to take each entry here and we want to figure out, we want to do the sign here, so sign times the entry, and then we want to kind of cross out the rows and the columns that that entry is in and write whatever's left. So this guy here, this is the whatever's left. Okay, and then same thing for all of the other entries of the matrix. Okay, so yeah, that's the main idea here. And we want to expand also along the first column. Now, the first column, it's going to be the same thing as doing it from the second row. So I'll rewrite the matrix here. Okay, so first, yes, you can expand along rows and columns. So I guess that's the main point of what they're trying to get you to notice here. 2, 1, 3, and 2, 1, 1. So it looks like this. And if we're expanding along this first column here, then we're doing the exact same thing. Okay, guys, so we have our plus, minus, plus, our minus, plus, minus, and our plus, minus, plus. We get something that looks like, well, our first entry here, we've got a 1. So, and we know it's a positive 1, so we have 1, and we're going to times it by whatever's left. So we're going to cross out the row and the column that 1 is in, and we're going to say, okay, what's left over? Well, these guys are left over. So we have 1, 3, 1, 1, okay? And then we move on to our next entry. So our next entry here is this guy, and we see that it's negative. So we've got to add the negative 2. And then same sort of thing. We cross out the column, and we cross out the row that guy's in. And we try to see what's left over. Well, these guys are left over. They're not crossed out. So we can go 2, 1, 1, 1. And the last guy, we have our positive 2 here. So we can add positive 2 and figure out, once we cross everything out, what's left. Well, I just erased like half the matrix, but we can figure out what's left by getting rid of those guys. And we see that we have 2, 1, 1, 3. Okay, and this is the same thing. You're still going to multiply it out the exact same way that we did before using this formula, AD minus CB, and you should. So this guy is asking us to find a determinant using row operations. So not doing cofactor expansion, the whole process thing that we just did. We just have to use row operations to do this one. So we got to do row reduction and somehow find out what the determinant is using row operations. Okay, so you guys should have learned in class that if you have any matrix of the form of this form, okay, or you have any matrix of this form, I don't know, I'm just making up a matrix here. So you have any matrix of this form where you have either all zeros in the lower half or all zeros in the upper half. Okay, so if you have like an upper or lower triangular matrix, then all you have to do to find the determinant of that guy is to multiply these numbers along the diagonal, and that is your determinant. So in this case, our determinant of this matrix would be 3 times 2 times 1. Okay, in this case, our determinant will be 3 times 5 times 1. Okay, so that's if they ask you to do it using row operations, they're definitely wanting you to find the upper or lower triangular matrix. Okay, so that you can just multiply these entries here. And it's really nice if you have something like that, because you don't have to go through that whole long process of cofactor expansion. Okay, so by now I'm sure you guys are getting pretty quick at row operations here, so I'll just go through this quickly. So what I'm gonna do is I'm gonna make it into an upper triangular matrix. So I'm gonna do a couple operations at a time. So I'm gonna go row 2 minus 2 row 1, and I'm going to go row 3 plus 4 row 1, and you guys can check and see if you did the same operations here. And so we have like this, and finally I'm going to go row 3 plus 9 row 2. Sorry, this is the worst 9. Okay, so I'm going to go row 3 plus 9 row 2, and I end up with 1, 2, 1, 0, negative 1, 0, 0, 0, 6. Okay, so you can see here that I have this form. I have the same form as this guy over here. So all I have to do is multiply the diagonal here. So I go 6 times negative 1 times 1 equals negative 6. And this is my determinant right there. Okay, so if they ask you to find the determinant just using row operations, that is definitely indicating that they want you to transform this matrix into an upper or lower triangular matrix. And then from there, just take the determinant by multiplying on the diagonal of the matrix. Okay, so this question here gives us a whole bunch of statements, and these statements are regarding determinants, and we have to figure out whether they are true or they're false. So the way we're going to go about doing this is we're going to try to either prove that it's true or to find a counterexample to show that the statement is false. So we're actually going to start with the whole counterexample thing on the first part of this. So in part A. So this one is asking us if we have a 3 by 3 matrix and the determinant is 0, then one column has to be a multiple of some other column. Okay, and offhand I know of a matrix, so I'm going to say that this one's false, because I know of a matrix that has a determinant of 0, yet the columns are not multiples of the other ones. So I'll show you guys right here. So it's just this matrix here, 4, 5, 6, 7, 8, 9. And when you work out the determinant, it actually equals 0. So I'm not going to do this whole thing out. You guys can check that for yourself. But this matrix has no columns, are multiples of each other. So for example, you can't take this column and multiply it by something to get this column, or similarly with all the other columns. So they're not multiples of each other, and yet the determinant equals 0. Okay, so this A question is false. Okay, so B, if we have 2 columns of a square matrix being equal to each other, then the determinant of the matrix equals 0. And this one is actually true. So why? Well, I'll give you guys an example of this. So if we have a matrix of this kind of form here, so where 2 of the columns are equal to each other, well, we can always do row operations here. So row 2, let's do row 2 times 1 over 2, and we get 1, 1, 1, 1, and then we do row 2 minus row 1, and so we get it of this form. So knowing this, you can expand along this bottom row here. So expand along the row of zeros, and you know that your determinant So the determinant is going to equal 0 in that case. Okay, so it's because, so this is true because you can always do row operations and you'll end up with a row of zeros, and because of that, you can always expand along that row, and so the determinant is going to be 0. So in this case, it's actually true. So that's something also to look out for. If you ever see two columns being equal in a matrix, then for sure your determinant's going to be 0. Okay. So next one here for A and B, which are two n by n matrices, so two square matrices, we have here the determinant of A plus B equals the determinant of A plus the determinant of B. Okay, so this one, let's do an example here where we take A to equal the identity matrix. And let's just, for simplicity's sake, also make B equal the identity matrix, okay? So we want to take the determinant of, first, of A plus B, so determinant of these two together. So A plus B in this case, we're going to have, we're adding A plus B, so this is going to equal determinant of 2, 0, 0, 2. Okay, and our formula for determinants is just AD minus BC. So we have AD minus BC, and so we have 4 minus 0 equals 4. Okay, so in this case right here, our determinant of A plus B is equal to 4. Okay, now we're going to take our determinants of A and B separately. So the determinant of A here, we use the same formula, AD minus BC. So our determinant is equal to 1, and our determinant of B is also equal to 1. So if we add the determinant of A, which we know is 1, and we add the determinant of B, which we know is also 1, we get 2. So in this case, is it true that 4 is equal to 2? No, it's false. So we know that we've proven by giving a counterexample that indeed this guy here is false. Okay. There's not much room for this question, so I'm just gonna erase after I finish. But you guys should write this down, the reasoning. Okay, so moving on to the next one, we have for A is an n by n matrix. So is this statement here true? Does the determinant of 3 times A equal 3 times the determinant of A? Okay, so I'm going to give you another example. So let's set A equal to 1, 2, 0, 3. Okay. And first thing that we're going to do is we're going to figure out what 3A is. So 3A is just going to be 3, 6, 0, and 9. And now we're going to take the determinant of this guy. Okay, so we're gonna figure out this side of the equation here. So we're gonna figure out determinant of 3A. So the determinant of this guy, 3, 6, 0, 9, is just 9 times 3 minus 0. So this is 27. Okay, now we're going to try and figure out this side here. So 3 times the determinant of A. So first of all, we'll go back here and we'll figure out, okay, what's the determinant of 1, 2, 0, 3, which is our A? Well, this same sort of thing, we have 3 times 1 minus 0, so this determinant is 3. Okay, but we have to multiply that by 3. The statement's telling us that we should multiply it by 3 to see whether these two here, these guys here, are equal to each other. Well, 3 times 3 is just 9, but we can see that, well, 27 doesn't equal 9, right? So in this case, we found another example that shows that this statement here is actually false. So this one here, this guy here is also false. Okay? So you can notice how we go about doing this is we try to think of examples, we try to think of counter examples to it, and usually we can figure it out that way. So here, what we're going to do is if A inverse exists, then determinant of A inverse equals determinant of A inverse. Okay, so with this one is actually true, and the reason is because so if we have determinant of A inverse, well, we know that the determinant of A inverse is equal to 1 over the determinant of A, right? Just from I guess elementary algebra kind of exponent rules here. So this here is equal to the determinant of A inverse, right? So this one is just kind of we've already been given this sort of thing. They're just trying to make sure if we remember how to actually do it. So yeah, this is true. The determinant of A inverse, so the inverse of determinant A is equal to the determinant of A inverse. So this guy here is true. Okay. F. So if B is obtained by multiplying a single row of A by 4, then determinant of B equals 4 times determinant of A. Okay, so this guy here is actually true. Okay, and I'll show you guys why it's true. I'll give you an example. Okay, so we're going to use the same A that we used before, 1, 2, 0, 3. And so that's our A. We're gonna create B by multiplying a single row of A by 4. So let's just choose row 1. So we multiply that by 4, and we end up with our B. Okay. So the determinant of A here. So determinant of A is just 3 times 1 minus 2 times 0. So it's the determinant of A is 3. Okay, determinant of B equals 4 times 3 minus 0 times 8, so it equals 12. Now, this is telling us that, okay, the determinant of B equals 4 times the determinant of A. Well, let's check that. So the determinant of A is 3, and the determinant of B is 12. So here we get x equals 4. So in this case, yes, it's true that the determinant of B equals 4 times the determinant of A. Okay, and so with this one, yeah, so this one is true. And the reason it's true is because we can kind of think about the factoring out this 4. So if we had a row like we had, I don't know, 2 and 4 and then 1 0 or something, if we took out a 2 from this first row here, and we ended up with 1 2 1 0, in the determinant, what we would have to do is since we took out the 2, we would have to multiply the determinant by 2 after. So you can kind of think of it like factoring, just like normal factoring of polynomials in this sort of way. So because we multiplied only one single row by 4, we know that we took out a 4, so in the end we have to multiply it back by the determinant. So that's why this one works here. Okay, for A, an n by n matrix, determinant of negative A equals negative 1 to the n determinant of A. Okay, so this one here is true. Okay, and the reason why is because we have our rule here. If you guys remember, it's determinant of Ka equals k to the n times determinant of a here. Okay, so this one is just comes from our rule that we were using, and so the determinant of negative a. So the determinant of, in this case, our k is our -1. Equals our -1 to the n times determinant a. Okay, so in this case, our k is -1, so we just are using our formula, our determinant rules here. Okay, that's why this one is true. H here is true. Here, I'll write it in red. So this one is true. Okay, this one is kind of similar using determinant rules. So if we have determinant of A transpose A, okay, we know that we're able to break up these determinants. So I guess I should do that in different order, A transpose A. So we know that if we are multiplying matrices together, then we can kind of split them up into, it's the same thing as, so multiplying them together and then taking the determinant is the same thing as multiplying or taking the determinant and then multiplying them together. Okay, so these two are the same. So, and we know that another rule that we know is that A transpose, the determinant of A transpose is the same thing, is equal to the determinant of A. Okay, so we can just rewrite this as determinant of A times determinant of A. Okay, and this is determinant of A squared. Okay, and because just from rules where if we have, some numbers to the squared, even if it's a negative number squared, we know that it has to be greater than or equal to 0. Okay, because if you have, I don't know, -2 and you square it, then you end up with a positive number. Okay, so any number here, even if the determinant is negative, when you square it, it ends up being a positive number, or 0, if it was 0 to begin with. Okay, so that's why that guy here is true. So it's really just remembering these, when you try and do these sort of proofs, it's remembering your matrix rules. Okay, so those are pretty important things to remember. Okay, and now we're finally on the last one here. Cramer's rule is useful for finding solutions to systems of linear equations in which there is an infinite set of solutions. Okay, so Cramer's rule is essentially we're finding solutions using determinants. Okay, so in this case, we know that this has to be false because we're using determinants to find systems of linear equations. Well, what do we know about determinants? So if we have an infinite set of solutions, okay, then we know that the determinant is equal to 0. Okay, so in this case, we know that we can't use Cramer's rule to solve a system of equations that has infinite set of solutions because we can't even use the determinant here. Okay, so we've made it to the last question here, and this question is asking us to find the inverse of this matrix using the formula which involves the cofactor matrix. Okay, so first of all, we have to determine whether the matrix has an inverse by figuring out whether the determinant is non-zero. So a rule of thumb is if the determinant of a matrix is non-zero, so if it does not equal 0, then the matrix has an inverse. And so if it does have a determinant equaling 0, then it doesn't have an inverse. Okay, so that's the first thing that we're asked to find here. So we will do that right now. So we have 1, 2, 0, 0, 2, 1, 3, 1, 1. Okay, and we have to choose a row to expand on, and I'm going to choose the first one because we have a 0 here, so it makes it a little bit easier. So what we have is same thing that we did above, is we're going to expand along all these entries here. So we're going to start with our first entry. So we have our first entry is a 1, and if we draw in our signs like we did before, we know it's a positive 1. So we have 1 times, and remember we kind of squiggle out the column and the row in which that entry is in, and we see what we have left. So in this case, whatever is left is this guy. So we have 2, 1, 1, 1. Okay. Our next entry that we're going to focus on is this one here, and we know that it's a -2. So I'm writing -2, and we kind of squiggle out the row and column that it's in and see what we have left. And in this case, we have these guys left. So we have 0, 3, 1, 1. Okay. So our next one is 0, and because 0 times anything is just 0, we can leave that one out. So we would just have, for example, we'd have 0 times something, but this would always equal 0, so we just are going to leave that one out. So here we have 1 times, and using our formula for determinant, we're going to have 1 times 2 minus 1 times 1. Then we're going to have -2 on the outside here, and we have 0 times 1 minus 3 times 1. Okay, so we end up with 1 times, and we have 2 minus 1, which is just 1, minus 2 times, and this guy here is a 0, this guy here is a 3, so 2 times -3, so we have -3 here, and this ends up being 1, and minus 2 times -3 is just +6, so our determinant is equal to 7 here in this case. So determinant of A is equal to 7. So because this doesn't equal 0, we know that A does have an inverse. So A has inverse. Okay, because the determinant's non-zero. So we've figured out the first step here. So now what's left is we have to find our cofactor matrix. So the reason that we're doing that, so I'm just going to write here determinant of A equals 7 so we don't forget. So you guys probably have been given the formula here in which it states that A inverse is equal to 1 over the determinant of A multiplied by the adjugate of A. Okay, so the adjugate of A is just the transpose of the cofactor matrix. Okay, so the transpose of the cofactor matrix, which means that we have to find the cofactor matrix. So if you don't remember what the cofactor matrix is, that's fine, because we're going to be doing it right now for A. So we're going to try and find the cofactor matrix of A. Okay, so what we're doing here is we're going to use our formula, our sign times whatever's left. Oops, put the apostrophe in the wrong place there. So our sign times whatever's left. We're going to be using that to find cofactor matrix. Okay. So what we're going to do is go through each single entry here, and we're going to just use that formula, sign times whatever is left. Okay, so let's start here with our first entry. Okay, so our cofactor position 1, 1. Okay, so we know that because of our signs that we figured out, this one is a positive 1, so we just have 1, so positive 1 times whatever is left, and in this case, if we squiggle out these, we end up with 2, 1, 1, 1. Okay. And when we compute that out here, we have 2 times 1 minus 1 times 1. Okay, so 2, we have the AD minus BC, so 2 times 1 minus 1 is just 1. Okay, so our corresponding entry in the cofactor matrix is just 1. Okay. next one. So our second entry here we're going to do. So we know that this one is negative. So when we do our cofactor matrix, we're not taking into account what the actual value is here. We're just using sign times whatever is left. Okay, so that's why I have a -1 here instead of a -2. When you're computing determinant, you have to take into account that this one here is a negative, or this one's a 2, so it's going to have a 2 in front, not for cofactor matrix. Okay, so in here we have a -1, and we're still doing, we're still multiplying by whatever is left. So we're getting rid of that, and in this case we have 0, 1, and 3, 1. So if we do this one out, we can see we have -1 times 1 times 0 minus 3 times 1. Okay, so we end up with -1 times -3, and that equals 3. So our next entry in the cofactor matrix is 3. Okay, and we're going to continue on this same way. So I'll do one more so that we just know what we're doing here. So our last one is our entry here, which is C13. Okay, so once again, we're kind of ignoring that there's a 0 in here because we're just concerned about our sign times whatever's left. So our sign in this case is positive, so we have a +1, and whatever is left ends up being, when we squiggle these guys out, so it's 0, 2, 3, 1. Okay, and that ends up being 1 times 0 minus 3 times 2, and that ends up being -6. So this guy here is -6. Okay, and we do that the same thing for all of these entries, all of the rest of the entries here. I'm not going to do that because I think that you guys you get the point of what we're doing. So I'll let you guys verify the rest of these by yourself, but I'll just write out what it actually equals here. So this guy right here is our cofactor matrix, okay? And now all we have to do, because our next step is we have to find the inverse. Okay, so using this formula here that we're given, we have to find the inverse. Well, all we have to do here is figure out what the adjugate of A is, which is equal to the cofactor matrix transposed, right? That's just the definition of adjugate A. So if we transpose the cofactor matrix, we get, so we just, and remember transposing is just when you write these rows in the columns. So this becomes 1, 3, -6. This becomes -2, 1, 5. And then we have 2, -1, and 2. Okay, so this is our adjugate here. This is our adjugate matrix. Oops, that's definitely not a highlighter. Adjugate matrix. And so all we have to do is to find A inverse is just plug it into the formula here. So we found out that our determinant of A is 7. So we have 1 over the determinant of A, and I'm using this guy right here. So our formula. So 1 over 7 times the adjugate of A, which we just found is this guy here. Okay. So once you multiply the 1 over 7 in, that's what our A inverse ends up being. So I guess I can write it out quickly. I'm sure you guys can multiply the 1 over 7 in here, but I'll just do it so that we have a final answer. Okay, so I'm just multiplying the 1 over 7 in. So this guy right here is our A inverse. Okay, so that's how you go about using this formula. First, you have to verify that yes, our matrix in question actually has an inverse, and this is by determining or making sure that the determinant is non-zero. In our case, it was non-zero. Then you're going to find the cofactor matrix by simply doing your cofactor expansion along each entry here, and using sign times whatever is left. And once you figure that out for all of the entries, you just transpose it, and that's your adjugate. And then you're just using this formula here. A inverse is 1 over the determinant A times the adjugate A.